Hi everyone, this is my second video in my series on proof, and in this video we're going to be looking exclusively at proof by exhaustion. So this is our third type of proof that we've looked at so far, and it relies on this idea of breaking an infinite number of things to check into just a finite number of cases. So the first slide here I've got just has some notes for you to maybe take note of. And I'm starting by saying that it is indeed impossible to check an infinite number of examples. Okay, we're only human. Even if you've got a bunch of time on your hands, it's an impossibility to do. So the idea behind proof by exhaustion is that you break this and split the proof into a finite number of cases. Normally this is, at most half a dozen in an exam because they're not going to want you to be there all day checking hundreds of cases. And then you systematically check all cases separately. And if all of those cases work, then your proof is complete because you've checked everything by including them in those cases. Okay, before we see some specific examples, I'm going to give you a couple of tips as to how these proofs tend to go. And that's you want to be always thinking about parity. And parity is whether a number is odd or even. Okay, a lot of these proofs are going to involve number theory type questions that are to do with showing that things are odd or even, or showing that something is divisible by a certain number, and keeping that in mind is going to be really useful to you. Okay, so think about parity. As well as that, we can think about division with possible remainders. So if we're not dividing by 2 and thinking about the remainder there, you might be expected to think about divisibility by another number. So for example, if you're thinking about divisibility by 3, then every integer n is of the form either 3k or 3k plus 1, or 3k plus 2. And together they represent all the different options because 0, 1 and 2 are the only remainders that you can get when you divide something by 3. Okay, and as we see more and more examples, you'll kind of get to grips with which to use and how that is all meant to work. My second tip is to do with checking that a number is prime, which happens quite a lot as well. So if you've got a big number and you don't know if it's prime or not, it's worth knowing that to show that a number is prime, you've only got to check certain prime factors. You don't need to check every single number to show that it doesn't divide into your big number. You've only got to check primes up to the square root of n. Okay, and that's because if you can find a small prime factor, then its partner factor, if you like, is going to be bigger than the square root of n. So there's no point in checking numbers bigger than the square root because they'll have a smaller partner. Okay, so as a quick example then, if you want to check if 131 is prime, then you take its square root. The square root of 131 is a bit bigger than 11. So that means you've only got to check primes up to 11, which are 2, 3, 5, 7, and 11. And as you go through, you'll notice none of them will divide 131. And that will mean then that 131 is prime. Okay, I think it's time then to look at some examples. I've got 5 that I think are increasing order of difficulty. And I'll talk through them and I'll show you exactly what you need to write down to get these proved. Okay, my first example then. What you might want to do before I show you the solution is to have a go yourself, pause the video, and then I'll come back and I'll give you the solution in a moment. Okay, hopefully you've been brave there and have had a good go. So we're looking out for keywords here in the question. If you spot certain kind of prompting words, it will kind of give you a clue as to how to proceed with your cases. So we've got here that n squared plus n plus 1 is odd for all integer values of n. Okay, this notation here is talking about n being integers. The word odd here is kind of suggesting what our 2 cases are going to be here. So it's probably to do with parity of n, isn't it? As it is, I can't really show that this is an odd number form, right? Where odd numbers are 2 times something plus 1. So I'm instead going to split my n into 2 different cases. So here they are. So firstly, we're going to show if n is even, then that means I can write n using the definition of an even number. That means that n is 2 times k, where k is obviously some integer. Then if I run it through this expression here, I'm then meant to show that I'm going to get an odd number out. So let's have a look at that. So this will be 2k all squared plus 2k plus 1. That's then 4k squared plus 2k plus 1. And then to show that that's an odd number, you need to be able to show that it's 2 times something plus 1. And I can easily do that. I can take 2 out of these terms and I get 2k squared in the bracket plus k, and then we're done because this is odd. Okay, so case 1 is proved. I've now got to do it with case 2 where n is odd, and then we're finished because together we've covered all integers because all integers are either even or odd. Okay, so I'll whiz through this and it's going to be very similar. N is odd. That means that n can be written as 2k plus 1. You can use minus 1 if you want, but I tend to stick to 2k plus 1. Okay, so what happens when you stick it into this expression then? You get 2k plus 1 all squared plus 2k plus 1 plus another 1. Expand it out, you're going to get 4k squared plus 4k plus 1. That's the first bit squared out. And then plus 2k. And then I'm going to combine these ones into 2. Then I can do a bit of tidying up. I've now got 4k squared plus 6k plus 3. But I'm trying to get an odd number, so really I should be keeping a plus 1 off to the side here. So I'm now going to think of this as 2 plus 1 again. Maybe I shouldn't have combined these quite so hastily. So I'm going to now take out a factor of 2. I'm going to borrow a plus 1 out of this plus 3 to turn it into a plus 2, and then I can factorise out of 2. So what's this? 2k squared plus 3k plus 1, because that will give me a 2 on the very end, and then there's the extra plus 1. And then we're done. Okay, so that's all you need to do there in order to show that, that proof all the way through. Okay, example 2, an example from antiquity here. We're going to prove that 2 to the 2 to the n plus 1 is prime for 0 less than or equal to n less than or equal to 3. Okay, so as I said, quite a famous problem that goes back quite a few centuries. If you can find a prime number of this form, it's worth you knowing the name of them. This gives you Fermat primes, if it's a prime. Okay, no prize for guessing who came up with that name. Okay, so because we've got a restriction here on n, that allows us to only check those 4 cases that we're given. Okay, we don't quite know yet what's happening beyond n equals 3, but we're only supposed to check these ones. So we have to do those in turn. So starting at the beginning, n equals 0. Let's plug it into our expression. So we've got 2 to the 2 to the 0. Remember that without brackets, we're working top down here with our power tower. We're starting at the top and working our way gradually down. So this is 2 to the power, and then 2 to the 0 is 1. Oh, I've got the plus 1. There you go. 2 plus 1 plus 1. That's 2 plus 1 is 3, and 3 is prime. So that one is checked, and it works. Okay, now n is 1. We've got 2 to the 2 to the 1 plus 1. That's 2 to the 1 at the top is 2 squared plus 1. 4 plus 1 is 5, and that's prime again. N is 2. 2 to the 2 to the 2 plus 1. That's 2 to the 4 plus 1. And that's going to be 17. And yep, 17 is prime. Then n is 3. Final check. 2 to the 2 to the 3 plus 1 is 2 to the 8 plus 1. And that's going to give you 257. Okay. Now, I'm not quite sure if 257 is prime. So I'm going to use my trick on my previous slide that I showed you. So I'm going to work out the square root of 257. And that's about 16.03. So that means I've only got to check primes up to 16. Or any prime that's less than 16, I should probably say. So let's check 2, 3, 5, 7, 11 and 13. Okay, so clearly it doesn't divide by 2. If I add the digits, that's going to be 14. That doesn't divide by 3. It doesn't divide by 5. It ends in a 7. I can check on my calculator if it divides by any of these, and it won't. just to save a bit of time. So if these have all failed, then 257 is a prime. Okay, so we're done. And we've shown it for all of the cases that we're meant to show. It's maybe worth doing the next couple, just to kind of show how this continued when it was first kind of looked at as a problem. So n is 4, it turns out will still work, you still get a prime. So the next one gives you a big humongous number. It gives you 4,294,000,000. Sorry, no, it doesn't. I'm looking at the next case. Give me a second. The next one gives you 65537, and that is a prime. So up until n equals 4, it was believed that this expression is always going to give you a prime because of the evidence that we've got at the beginning. But it was thanks to Euler that it's the next one that gives us a non-prime. So this is where it breaks down. So the next one is the number I was about to say, 4,294,967,297. There you go, I did that all in my head. And it turns out this number is obviously 641 times 6700417. So it's not prime. Okay, but you obviously knew that, didn't you? Okay, quite a nice example, and it involves being given the cases themselves to check, so that's quite nice. Okay, example 3. This is quite a famous one, quite a good example to kind of get you thinking about how to approach the cases, and it has turned up in a couple of exam pass papers, so it's worth knowing this one. It's quite an important one. We're proving that all cube numbers are either equal to 1 more or 1 less than a multiple of 9. Okay, so again, if you think you've got a way of getting a proof written for this, then have a go, pause the video, and I'll go through the solution in a second. Okay, welcome back. So let's have a look about how we might approach this. We're looking at things being a multiple of 9, or something similar to a multiple of 9. So it might be useful to think about division with remainder. My division with remainder trick I said in a couple of slides ago. Now, thinking about remainder when you divide by 9 is going to give you quite a lot of cases. So that's probably not going to be the most efficient one to use. Similarly, using parity, thinking about my cube being something like 2k plus 1 cubed or 2k cubed for odds and evens. You can try that, but what it's going to produce won't be anything that looks like a multiple of 9. You're not going to get many 9s out of cubing out these expressions here. So parity doesn't look like the way to go. So it turns out that the best way to approach this is to split into 3 cases, and that's to do with division and remainder when you divide by 3. So this is how the proof's going to go. So we're going to consider my cube number first of all, and my cube number is going to look like n cubed. So we're thinking about the remainder when you divide n by 3, okay? And then cubing those expressions will be what gives you these multiples of 9. So we've got case 1. That's n is a clean multiple of 3, okay? So in this case, we can cube our expression. So n cubed is 3k all cubed, and that's going to give me 27k cubed, and we're looking for one of these 3 options, and we've got a multiple of 9, so we're done. So that's 9 lots of 3k cubed, which is good. It's a multiple of 9, and we're done. Okay, case 2. What if n is 1 more than a multiple of 3? So that's 3k plus 1. So again, we can cube this out, collect up some 9s hopefully, and we might get one of the other cases I'm expecting. So we're cubing out 3k plus 1. If you know your binomial theorem, you should be able to do this. So this is 3k all cubed, and then 3 times 3k squared, and then 3 times 3k to the 1, and then plus 1 cubed, like that. Okay, so I've expanded that out. Let's simplify it. So that gives you 27k cubed. This will give you 27k squared, and then you get 9k plus 1. Okay, now I'm running out of space here, but I'm meant to fit it on here. So let's take out the 9. And then you've got 3k cubed. You've got 3k squared. You've got plus k, and then plus 1 on the end, which means that this expression here is a multiple of 9 plus 1. So we're good to go. We've got one more than a multiple of 9. Excellent. Okay, case 3. Our final case is when n is 2 more than a multiple of 3. If you like, it might be worth you doing 3k minus 1, because that's equivalent to saying that it's a multiple of 3 plus 2. But I'm going to stick to doing 3k plus 2. Okay, right, let's finish this off on the same page. So n cubed is 3k plus 2 cubed. Okay, so I'll save you the time of cubing that out. What you're going to get is this. You're going to get 27k cubed plus 54k squared plus 36k plus 8. Now, using a similar trick as before, I want to end up with, I'm expecting probably the one less than case, because that's the one we haven't had yet. So if we think of 8 as 9 plus 1, or I should probably say 9 minus 1, because that's correct, then here's the minus 1 I can tack on the end, and then this 9 can be factored out with the rest of these terms here. So then finally we've got this. We've got 9 times 3k cubed plus 6k squared plus 4k plus 1, and that gives me my plus 9, and then here's the minus 1 on the end to finish the proof. Okay, so in all three cases we got one each of these cases that we were trying to achieve, and we're done. Okay, let's move on to example 4. I've got 2 more, and then that'll be the end of the video. Right, so we are now moving on to prove part of a quite famous and quite beautiful formula here. So we're proving that, and I'm using sigma notation here, which you'll recognise from when we did sequences. And I think it's worth us putting one of these examples in so you're kind of really familiar with how this notation works. So remember that this sigma is the sum of, so it's the sum of r cubed, where r goes from 1 to n, and that's equal to the sum of r, where r goes from 1 to n, and that's all squared. And we're going to show that's true for 1 less than or equal to n, less than or equal to 5. All right, so before we begin, let's take a note of what this says properly. So the expression here is the thing that we're adding up. So we're adding up these, r cubed, and then this tells you where to start. That's when r is 1, and this tells you where to finish. Okay, and then bear in mind over here, you've got a little bit of BIDMAS in that you work out the sum first in the brackets, and then you square after you've worked out that sum. Okay, right, let's start with n is 1, and we'll see what happens. So on the left-hand side, we're starting with r is 1, and we're finishing where we started at 1. So let's write this. R is 1 to 1 of r cubed. Well, that's just 1 cubed. There's only one term in that sum there. Okay, now that's 1, and I'm hoping it's the same on this side. So the sum from 1 to 1 of r all squared. Well, in the bracket is just one term, and that's 1. And I square that and I get 1, and we're good. Okay, n is 2 then. So the sum from 1 to 2, that's my n this time, of r cubed. So this is the sum of the first 2 cube numbers. This is 1 cubed plus 2 cubed, and that's 8. And then on the right side, we've got the sum from 1 to 2 of r, all squared. So in the bracket, we've now got 1 plus 2, and that's 3 squared, and that's 9. And I've made a mistake. I've just noticed this is 1 plus 8, this is 9 as well. Okay, great. So they're the same as well. I'm going to do 3, and I'll leave it to you as an exercise to finish off the last 2 cases as well. So when n is 3, we have the sum from 1 to 3 of r cubed. That's 1 cubed plus 2 cubed plus 3 cubed. And that is going to give you 36. I'm confident about that this time. On the right side, you've got the sum from 1 to 3 of r squared. That's 1 plus 2 plus 3, all squared. 1 plus 2 plus 3 is 6. Square it, you also get 36. Okay, so I'll leave the rest for an exercise. We've proved it up until there, but you do the last 2 just to finish it off. Okay, my final example, I'm not going to go through all the way through, but if you want to have a go at a challenging one, I can leave that to you. So we're going to prove that n to the 7 minus n is always divisible by 7. Okay, and assuming here that n is going to be an integer. So this is quite tricky. It's not immediately obvious what to do, but seeing as it's divisible by 7, it seems as if we're probably going to look at remainder when n is divided by 7. Okay, so the first thing I'm going to do is I'm going to write this in a form that looks a bit more manageable. So I'm actually going to factorize this because raising something to the 7 is kind of tricky to do, particularly when your expression is quite complicated. So let's factorize. Okay, so n to the 7 minus n. Well, firstly, I can take out a factor of n from that. These with this. And then eagle-eyed students will notice that this is in fact a difference of squares. N to the 6 is n cubed all squared, and then 1 is of course 1 squared. So this is a difference of squares. So I'm now going to split this into 2 more brackets. The first of which is going to be n cubed plus 1. The second of which will be n cubed minus 1. Okay, good. Right, so you might think that we're going to stop here. Well, actually, the sum of cubes and the difference of cubes also factorizes. And I'm going to write that down over here so we know what's going to happen next when I do the next bit of factoring. So it's worth knowing these off by heart as well. So x cubed plus y cubed is firstly x plus y, and that's multiplied by x squared minus xy plus y squared. Okay, that's the way to factor the sum of cubes. And then the difference of cubes is very similar. That one is x minus y, and then it's x squared plus xy plus y squared. Okay, so that's a nice piece of factoring that we can now take note of and use. I'm going to apply that to my brackets here with n. Just bear in mind what we've got here. So x is replaced with n, and y is replaced with 1. So I'm now going to have this. So n. And then the first of these is going to be n plus 1, and then n squared minus 1n, which is n, and then plus 1. And then the difference of cubes will be this, will be n minus 1 times n squared plus n plus 1. Okay, so now this is fully factored, and what I might want to do now is rearrange the terms to kind of put the things that want to go together. So this is n plus 1, n minus 1. That's the nice ones all together, and then these are the two. N squared plus n plus 1, n squared minus n plus 1. Great. Okay, so these are 5 different factors that we can use to figure out what this entire thing is divisible by. So now your cases, well, as I said before, will be what happens when you divide n by 7. So first case is n equals 7k. And then we're going to get 7 cases total. So let's write these down. I'm going to actually do dots to save a bit of time. So this is case 7. So next case is n equals 7k plus 1. N is 7k plus 2. All the way down to the last one, which is n equals 7k plus 6. Okay, so if you want to finish this proof off, all you've got to do is check these 7 cases. And in each case, all you've got to do is show that one of these 5 factors that you've got here is divisible by 7. Because if one of the factors divides by 7, then this entire product will then divide by 7. So not as much work as you might think from here on. You've just got to see which factor you think will be the one that will divide by 7. Okay, I'll leave that to you if you want to finish that off as a bit of an extension question. I'll finish writing the notes. If you want to take some notes down, then you can. Hopefully this video has been informative to you, and I'll see you in the next video. So for now, I'm just going to finish this off. Check each case. One factor should divide by 7. Okay, right, best of luck year 13. Hopefully you've enjoyed that, and I'll see you soon in the next video. Bye now.